Hello, everybody. My name is Servesh, part of the Radiation Computing Facility and the Performance Engineering team at ALCF. So before we begin the talk, I just wanted to give you a quick overview of what we're going to focus on this presentation, right? Because Aurora is there's lots of different topics that we could talk about and explore. But for today, I want to give an overview of the system, and then I would very narrowly focus on the compute blade itself so that I can hopefully do a good job of highlighting the different nuances, and that gives the programmers the perspective of what they need to keep it in the back of the mind when they optimize or program or run their applications on the system itself. Okay, so with that, I will go ahead at the first slide. Okay, so this slide, there's lots of numbers in this slide, but it tries to give you in a one slide overview of the entire system, its features and characteristics. This is a standard slide that we presented elsewhere, but just wanted to give this as a form of introduction to the entire system. The key thing is Aurora is a GPU-based supercomputer, right? Like many supercomputers that exist today. So we have the Intel Xeon CPUs and the Intel Max series GPUs, 6 of them for GPU and 2 of them for Xeons. Those pretty much give us the core compute power for the entire system. Apart from that, some interesting things that we have is the DAOS storage system, which is an all-flash storage system with persistent memory. So that gives you quite a bit of robust I/O. We also boast one of the largest amount of memory and the bandwidth that it provides in a system of this scale. For the network side, we use the Dragonfly slingshot network with the Dragonfly topology. And the numbers are there for the peak intersection and bisection bandwidth. It's stated to be peak of over 2 exaflops. So that's the stated compute power for the entire system. So we support the entire OneAPI SDK and its various programming models. Predominantly that covers SYCL and OpenMP with the other portable layers such as COCOS. So moving on, this is 3 slides. I've tried to give an kind of a breakdown of how we group the system together, right? So to start off with, the entire cluster is organized as blades, chassis, and racks, right? So we have about 166 racks in total. In that, we have several chassis, 8 of them per rack. And then within that, we have the different compute blades and the switches. So this is typical to any other KEX platform type cluster right now. It's a very dense form. The square footprint to the compute power, it's quite massive and quite intricate by design. On the surface where users interact with the system, it's basically they only see the login nodes and the storage nodes. But there is a lot of backend service nodes as well that operate to try to support and try to run the cluster itself, right? So this is the overall picture where it shows how the blade, the compute blade and the network blade is put together, and then it forms the rack, and then it overall composes of the entire system. Okay, so for the purposes of this presentation, we will try to go into as much detail as possible into the compute blade itself. I will try to present in the coming slides further details on each of its components, how the code execution happens on the GPU. Also, I will try to present on the data flow layouts and the different data movement options that are there in the platform itself. On the left-hand side, again, it's a one table overview of all of the different bandwidths and memories that we have in the compute blade itself, right? And then some amount of data to the fabric itself for the injection bandwidth that we get. So this diagram, don't worry about it. I'll talk about it in a bit more detail in the coming slide, but just to give an overview of all of it together as a reference deck in the future. That's why this slide is put together like this. Any questions at this point? Because after this, we'll start moving into the content itself. Okay. Okay, so as I said, right, I'll focus a lot on the compute blade, but I wanted to talk a bit about the network itself, right? Because it's quite unique. There's 2 slides to it. This slide just talks about the kind of components, and the next slide talks about the topology. So we use something called as the slingshot network, which basically allows us to have like a sufficient number of endpoints to meet the injection bandwidth that we need to run the system. 2 main components exist. One is the NIC itself that's based in the host. We have 8 of them. The other is the switch, which resides per chassis, which basically connects it in the Dragonfly topology to compose of the entire system. So Slingshot boasts some of the most advanced congestion control and adaptive routing. So it gives applications that are running together in the system to try to balance out and try to provide different scheduler classes to allow for communication to happen without interfering with each other. There is also a lot of features that require to work with other parts of the system, like so basically Ethernet overlays and stuff. So that's the part of it. For the application side, like, where they will benefit from is the hardware engine to do the flow control and the track matchings. So those really helps. Our Dragonfly topology, similar to other system, is a 3-layered one. We have an all-to-all connectivity within the rack itself, the chassis itself. But then there are global links that tries to connect to the rest of the system. So we have about 165 total groups, which is basically divided into 166 compute, 8 IO, and 1 service group. Some numbers on the injection bandwidth and the bisection bandwidth, which I showed earlier on the slide, just to give you an highlight into it. Again, there's lots of details to go into the network topology itself, but I wanted to try to just set perspective to it, but I will further focus only on the compute plate itself for this presentation. Okay, so before I go into this, I tried my best to illustrate with various diagrams to try to reference out how the execution flow happens both on the GPU and the data flow happens across the entire plate itself. So first, one second. So first, let's just talk about the CPU, right? Because this is essentially like the component that tries to interface between the GPUs and the NIC and tries to be essentially like the fundamental component to the data movement between the entire system. So typically, when CPUs are presented, the application side view is they have like distinct compute components, like the different ALUs and the vector units and the caches, and they tend to be just put together into like a monolithic die, right? The Xeon CPUs, the Max series CPU, the Sapphire Rapids, codename with this one, it's actually like composed of distinct dies that are put together. A diagram here. I will talk more about the diagram in the later slide deck, but just to keep in mind that it's not simply a component distributed over a static standard monolithic person. So there is like lots of intricacies in how the bus operates and how the interconnect between the different cores also operates. There is also different NUMA regions, and we can operate the SPR in different modes. So you have like the basic flat mode or the quad mode, which basically lets all of the quadrants be visible. There's more like SNC and stuff similar to what we had in the Xeon Phi family, which allows you to divide the quadrants itself into distinct zones and then operate on them independently. Again, just to give a preface of this, I will go into a bit more detail on the latest slide deck. Other things we have is we have like quite a bit of PCIe lanes, and they operate at Gen Phi. And one other important thing that we have is we have like a really high speed HBM based memory that's next to the CPU itself, in addition to the DDR that we have on the platform. So this gives us, I would say, quite large amount of memory that applications can take greater amount of advantage of too. Okay, so the core compute performance, like for Aurora, comes from the GPUs, the 6 GPUs that is present in the blade itself, right? This slide tries to talk about the GPU architecture. It tries to build upon how the processor itself is put together, right? So the fundamental compute comes as part of GPU comes from Xe cores, which composes of different vector and systolic units, a bit of cache. Those are all put together into a slice with connectivity between them. And then this is built up into a rack. Sorry, not a rack, a stack. And then for the GPU that we have on Aurora, it's actually a dual stack architecture. So we have two of these stacks through a stack-to-stack interconnect. In addition, there is the additional components that talk about like the HBM, the caches, and everything that overall is put together to form the compute construct as well. So some nuances that are unique to the Intel Xe GPUs is we have like a large amount of last level cache, right? Like around 200 megabytes of that. So that's like quite massive for the GPU of this era. We also have the unique connectivity between the GPUs and the stack architecture. Those are all like kind of very specific to how it works on the system. In addition, there is also the concept of how we utilize that for the application. We have the ability to use it as an entire GPU, or we could break it down into subcomponents and to target them for specific code blocks. I'll talk a bit more once we go through the architecture, like, you'll get to understand a bit further on that. So here, I've tried a bit to illustrate it in a bit of a block diagram, how the compute execution in the GPU itself happens, right? It's kind of similar to other vendors' GPUs, but there are some differences between how the scheduling and how the execution happens in the GPU that is in Aurora itself. Again, this is the Intel diagram. Like we have it in this link. Please take a look at the link to have more details on that. But I've redrawn it on the right side to basically make it easier for me to go through and explain the system. As I said before, right, we have the Xe cores that composes of the stack, and then the two stacks, and they are connected together via stack-to-stack interconnect. Each of the stacks have their own GPU to GPU Xe links. Again, the links come later in the slide deck, but here they are part of the architecture. There's portion of HBMs that are connected to each of the stacks. And then there's a particular PCI endpoint connected to one of the stacks, right? So then that's how the device comes to operation. The logical view of how the execution happens is the application is organized into a compute kernel, and then there's work group and work items that are scheduled onto the system itself. These compute items are broken into different GPU threads. And then using various command streamers, they are dispatched onto the particular compute units for execution. Once execution starts, it tends to either complete until the end of the thread instruction is received, or if there's a condition where there's a data operation or a stall that occurs, and therefore it switches to multiple threads and executes them in parallel. So all of the communication through the entire GPU happens through the what we call the L3 fabric, and through the backend logic that connects the caches and the links and the tiles together. And some other nuances is like when we have data existing similar to how we have in the CPU, if it's existing on the HBM that is on the same stack versus an HBM on an operator stack, there is going to be NUMA differences to see. So applications tend to either, if they are very sensitive to memory latencies, they tend to optimize it to a particular stack and then handle the allocations. If they're more throughput based, then you could potentially use the entire GPU's allocation and then try to just run through the kernels and fit across the entire or both the stacks to compute and execute. Also, there is support for atomics across both the stacks. So, but the caveat is that each of the stack has their own L3. So therefore, again, you have some NUMA differences there to account for. Any questions in this slide before I move on? Okay. So apart from the compute execution, majority of the other challenges and optimizations come from the data flow layout and optimizations that a programmer can do within the blade, right? Again, there is more you can do by moving data outside from the network itself, but even within the blade, there are lots of different parts and how data access patterns are done that could really benefit. So this is a blown up view of the earlier diagram where I try to highlight the different links. So to start off with, we have the two CPUs with their HBM and the DDR. They are connected together via the UPI links. We have 6 GPUs and they're connected via the XC-Link fabric. Each of the GPU has their own dedicated PCIe lanes connecting to the CPUs, 3 of them on each side to follow symmetry connecting between the two CPUs. And then they have, from the CPUs, you have 2 Gen 5 PCIe links going to a switch, which then breaks it out into 4 Gen 4 X16 lanes that connects to the 4 HPE Slingshot NICs on each of the CPUs. So, and then they go out to the fabric over, each of them have 2 ports with 200 gigabits, and then they connect to the fabric itself. So there are some critical differences here. We don't have a direct path of connectivity between the GPU and the NIC, but we can use the CPU to take it and bypass it and directly go to the NIC as well. So there are some advantages, disadvantages approach. One, it allows the CPU to do some optimizations. The disadvantage is that you don't have direct GPU to connectivity to the network. But within the 6 GPUs itself, the XC-Link fabric allows you to move, schedule, and run workloads or move data between them. So that's quite effective to use. All this is kind of hidden underneath the MPitch optimizations, which is the MPI library that we use for running the applications, and the specific application optimizations to try to utilize the effective path between them. Okay, so I will try to now go into each of the components and try to highlight some of its characteristics for the data flow specification, and then probably then come back and talk about the XC links as well later in the slides. So here is a blown up view of the CPU. I mean, again, more details are available in this link above here. The key thing for the Sapphire Rapids, the Xeon Max series CPU that we have on the Aurora blade is it's composed of different dies, and then you have a physical boundary connecting all these dies together. The entire mesh of this is connected through a SHA bus. So basically, if there needs to be kind of data movement that needs to happen between this portion of the quadrant to this portion, it has to go through this bus itself. It's pretty good at, like, you won't notice it, but if you were to overwhelm this this bus, you would see some bottleneck. So it's preferable to try to overlap and do asynchronous communication as much as possible. Each of these quadrants are connected to the respective accelerators. So that's why you see that, like, you do not have a common shared topology. You need to go through the bus itself to the data movement. And each of them have their own NUMA memory quadrants as well, connecting to the specific DIMMs and the HBMs, right? One important, yeah, go ahead.
There are a couple of questions I was wondering.
Yeah, we can pass here. Yeah, so go ahead.
Yeah, so I guess one discussion is, like, if the PVC are going to be available commercially outside of Aurora. I don't know.
Yes, there's a link on the Intel website, right? You can go and check it out. They have the specifications to buy them. Yes.
Okay, and then the other thing, there is a discussion right now in the chat that they're talking about which part of the GPU did you mention that is larger than any other GPUs?
The last level cache.
Okay. And then I think the last question is, do CPU and GPUs have cache coherency to enable zero copy?
I mean, like, cache coherency within the CPU itself is a bit of a question, right? Because it's not like there is no cost associated with it. They are physically distant, right? So yeah, in virtual cases and software libraries, you can claim there's cache coherency, but you are going to go through a PCIe link, right? So there is going to be latency associated with it. So to answer the question, there is actually no cache coherency, but there are software layers like shared memory transactions in USMs that allows you to mimic that behavior.
Okay, well, thanks. Yeah.
Okay. Yeah, I'm not sure whether I didn't put numbers here, but yeah, the L3 is the largest that we have on this GPU compared to other devices. Okay, so the first nuance of the GPUs that the users need to be aware of, as I mentioned, this is a dual stack or two different die architecture, right? So if you have to move data between one stack, the next stack, you need to go through a specific stack to stack interconnect, right? The application or the user doesn't need to do anything special for this to happen, but it implies that there is going to be a NUMA kind of a behavior that you will see when you target independent stacks, which is both the stacks together. That's why I said when you have throughput-based application, if you target both the stacks, you shouldn't have much of a problem. But if you're sensitive to memory latencies, then you need to account for this to utilize it better. There's also the caveat that the PCI endpoint that connects to the CPU is connected to the tile 0 of all the GPUs. So if tile 1 needs to communicate to the CPU, it needs to go through tile 0. So it will share the PCI bandwidth if you were to do transactions or memory movement between both the stacks at the same time. Okay, so bit of just wanted to, there's a lot of explanation, technical details you could go into, try to talk about the PCI switch. But I wanted to mention it here because it's important to understand that, like, you have particular lanes that are translated into the specific lanes that are for the NIC itself, right? So there is, like, even though there's a switch, it's quite transparent. The simple reason being we have a direct translation between the Gen 5 lanes to the Gen 4 lanes. Specifically, we have 2x PCI Gen 5 X16 lanes, which are electrically connected to the PCI switch. But virtually, they are broken into 4x Gen 5 X8 links, right? Which can be directly translated to 4 PCI Gen 4 X16 lanes, because each generation of PCI is just like a 2x of the previous generation. Sorry, was there a question?
There's just one question related to if the CPU is a NUMA domain.
CPU, if you use it in the default mode, the quad mode, you will only see one domain. If you have the SNC mode, you will see it as 4 domains. There is also the HPM that is present in the CPU, which will again has 2 different modes. One mode which allows you to use it as separately as the flat hierarchy. Another mode which allows you to use in cache-based, which basically hides the HPM underneath the DDR itself.
Thanks, Servesh.
Yeah. So, but within the switch, there's quite a complex set of transactions that needs to happen to translate at the physical layer itself. But the whole thing is, even though you have these translation on the system side, the 4 NICs appear as directly connected to the CPUs, and the users generally do not need to be too worried about why this kind of translation, if it affects the performance or anything as such. Okay, so now I try to go into the details of how the data flow happens for the different components. So let me start with something that is the most simplest thing, right? So you have like a piece of memory that is allocated in the DDR, and that has to be sent out through the network, right? So again, here is what I want to talk about, the SNC versus the quad mode, right? By the default, the quad mode allows the CPU to act as one single piece of domain, so one single piece of logic. So therefore, the users don't need to really be focused on trying to optimize where their memory is present. It'll try to give you a sufficiently good bandwidth. I'm going to mute a person. I think there's can you mute one of the people? Yeah, see, I think their mic is on.
Yes,
Yeah.
yes, let me see.
So when we have the allocation on this case, like, what happens is when the CPU wants to send this data over the network, so underneath the logic, what happens is a credit system is used. So basically, the CPU initiates a transaction and it says that, like, over the bus, it needs to communicate this much data to the particular NIC. So then what happens once the DMA transaction is initiated, you have the data movement that occurs from the DDR over the SHA bus, over the cores and LCs, and then it passes to the respective part of the CPU where the NIC is connected, and then the data flows out through it. So again, when you have you look at the system, you can do something like LS topo or LSPCI to understand how and where the network cards are visible to the different quadrants. When you go to SNC4 mode, it allows more control to the users. Basically, it breaks the CPU into 4 different quadrants, right? So then you have the 4 different domains. Then what happens is it gives you the ability to microscopically try to manage data movements. And this will be beneficial where in the cases where applications want to really fine tune the asynchronous data movement operation within the various dice itself. From what we have seen is generally larger applications that do not have a lot of sensitivity to where the memory is present or how the data is being moved. This is not much of a benefit. But some applications which are extremely memory bound, then this becomes like something that they could look at to optimize it further. But please do be aware that, like, it's, even though, like, it all appears to be a single die and everything is present together, there's physical limits, right? The physics is going to limit you based on where the data is there and how it's moved. And those are some things that you might need to look at depending on which applications that you try to optimize on this particular system. So now we go to a bit more of a complicated kind of data flow design where we have the CPU and the GPU, right? I have tried to highlight basically 3 different data locations and try to show you how it actually moves through to the data fabric and into the GPU itself. The first and simplest example is you have an allocation on the CPU, and it's a device allocation. It's not a shared allocation. So basically, that means that the user allocates all the memory on the DDR or the HBM, and then he wants to move that entire memory to the GPU memory. Okay, so in this case, the simpler of approaches happen. The DMA transaction starts, and then it goes out to a specific PCI link. For the GPU itself, what is unique is that in the case of the Intel GPUs, we have dedicated engines called as copy engines, whose sole responsibility is to move data between the host and the device, and even within the GPU to a different GPU, or even within the GPU as well. So those engines are used to whenever there needs to be large amount of data needs to be moved from the CPU to the GPU. So therefore, that kicks in, and then once data arrives through the copy engine, it uses the large fabric, which connects all of the components within the GPU to then move the data to the specific HBM location within the GPU. When there's a shared allocation, there is a nuance to this, because shared allocation means they need to exist between both the CPU and the GPU, and depending on when the application accesses them, the data then migrates back and forth to different hardware mechanisms like page faults or virtual addresses. So you will always get the most benefit by having dedicated allocations and manually managing memory, like any other GPU-based or multiple domain architecture. And this is no different to that. But shared allocations come into helpful case where you want to have, other than the amount of memory that is present on GPU, and then you want to, or you do not know which portion of the memory or a smaller portion of the memory is what you might use for computations, and therefore you are ready to trade off the performance penalty that you might incur from it. Now, the key thing here, in addition, is that, like, if, for example, if the memory doesn't exist on the CPU's DDR that is connected to the GPU, and it needs to come from a different CPU, then you really pay a penalty because you have to go through the UPI links that connects the two CPUs together. So that really would affect things. So preferably you try to map the memory and the allocations within the CPU that you're going to use for GPUs, and then try to keep it separate and do explicit movement, rather than trying to allocate memory across both the CPUs and then try to figure this out later during the operation on the GPU itself. In addition, within the GPU as well, if data movement needs to happen, it uses this fabric that's connectivity across all of the different slices and the different compute units. So that is also a key thing to know, because there is a limit to how much the bandwidth that you can operate on the fabric itself. Again, these are all things that you will notice if your application is extremely memory bound and latency sensitive rather than throughput based, right? But this is a common limitation for any GPUs that exist. So Yasi, I'll take a pass here. Any questions?
I guess there are a couple, but we can also talk
Finish at
about
the
it
end?
at the end of the day.
Okay,
At the end
okay.
of, yeah.
Okay. So now I wanted to illustrate how the data movement happens if you have an allocation that have to be streamed across the CPU, the GPU, and the network card. Okay, so there are two different colored arrows here. So for the first one is what we talked about in the earlier slide, where we have, like, for example, a piece of memory that is coming in from the GPU and it goes to the core of the CPU itself. Okay, so the users have two choices here. Either they can move this piece of memory into the CPU and then do some post-processing to the data itself before it's pushed out over the network, or bypassing the complete memory on the CPU, they can use the core's bus itself and then translate the data out through the network. The advantage of directly going out through the core bus without going to a piece of memory on the CPU side is you get, like, better latencies, but your throughput or the bandwidth is lower. Whereas if you were to basically move it to the host memory and then try to push it through the PCI switch and the network card, you get a higher bandwidth, but you pay the additional latency cost of moving it to the host memory. One advantage we have is basically by physical distance, right? We have the HBM that is allocated next to the GPU. Utilizing that will give you better latencies than going all the way to the DDR. But the limitation is the HBM is just, like, a smaller size compared to the DDR's larger set. So these kind of options gives the users the ability to fine tune how and where they want to the data movement within their applications to better utilize it. Okay, so with that, we have the network and the GPU and the CPU. So there's an important part of the system, which is also the GPU to GPU connectivity, right? So this is quite an intricate and a complicated system that exists within the Intel GPUs, right? So for example, as I mentioned, the copy engines earlier on, they can be used, and there are many of them that could be used to move the data between the GPUs as well. Underneath those links, there is, like, this high-speed serial deserializer and the connectivity that exists between the GPUs. And this is a fully connected network, but this is not fully visible to the users, right? So whenever a user needs to take advantage of it, they need to go through the application interfaces, either via the MPICH layers or the programming layers. And then that would allow them to basically stream data from one GPU to another GPU or one GPU to many GPUs. So this is just an example to show you the underlying components itself. When a user looks at this diagram, that could be implied that, okay, it's simplistic in design and it's just that all the GPUs are just connected between each other. But as I explained earlier on, we have a dual stack architecture, right? So, and then how the connectivity is done on the system is you have two different planes, right? 6 tiles on one plane and 6 tiles on another plane are connected to each other. But due to the way the physical organization of system itself, it's not necessary that all tile zeros of the GPU or all tile ones of the GPU could be connected, right? So you will get still 6 same GPUs connected in a single plane, but there are some topological differences and the placements that allow you to basically have this difference. In this slide deck, I try to highlight how that is in a bit of an illustrative manner, right? If you look at the red links of stack 0 of GPU 0, you will see it connected to basically stack 1 because that's the closer point that is next to it. Similarly, stack 1 of this GPU. But then if you go to this one, it's more of the stack 0. So therefore, that kind of implies that when you go for the dual stack kind of placements and application optimizations, and if the application is going to utilize the Exascale links to do the data movement explicitly, then what they need to do is account for the topological differences. And this is something that users can get from basically querying the topology status of the system itself. And from there, they could map it out. And this is a standard topology across the entire cluster, right? It doesn't vary from one blade to another blade. All blades have the static topology for the connectivity due to the electrical connectivity between the different GPUs itself. Another thing is when you have the tile, as I mentioned, right, one of the first stacks is only connected to the PCI endpoint to the host. So therefore, there could be some worst case scenarios where adjacent tile is where the communication really happens. And if you need to move the data from that to the host, it might need to go through the neighbor's stack or the different tiles PCI endpoint and then through the host. You could also optimize the data to always collect it on a single GPU and then push that out to the CPU as well. Again, for a specific source and a destination, there could be multiple different ways you can kind of connect and kind of move data between them. Okay, so Yasi, I will stop here and I think we can go through the questions and see if I could answer any of them better.
Yes. So I guess the first one was, will allocating buffers in HBM gives faster MPI communications?
Between what? Between the network cards or between the GPUs? Where is the important question, right? But at any point in time, HBM is going to have more bandwidth and lesser latency, right? Because it's physically closer to the GPU and the CPU, and then for both the cases. So maybe whoever asked the question can maybe specify which part they were trying to do, and then you can answer that again.
Yeah, he's asking about between the CPUs.
Yes, it will be faster because the amount of performance, the memory bandwidth is higher for HBM, right? So therefore, data, if you have large amount of data, then it's going to be faster with the HBM.
Okay. So the next one is, looking at all the network design, what do they mean to the average user? How do they compare to the other machines such as Frontier? And if they do, what do we need to know transitioning from Frontier to Aurora? For example, I don't remember whether GCDs are directly connected to network or whether they are connected like tiles through only tile 0.
So in the case of Frontier, the network endpoints exist within the GPU. The GPU and the network cards are directly connected. In the case of Aurora, that's not the case, right? So the CPUs are where the network are connected to. So that's why I said you have the advantage of using the CPU to do the data translation or packing that you might need to do to move the data off the system or off the blade itself. So you could argue that one or the other can be better specifically depending on the applications that you want to optimize for.
Okay, and I just also want to mention now that we're asking questions, if you guys want to ask questions, feel free to unmute yourself and ask, but I will go through the ones that is already in the chat. So The next one, Alfred is asking that a long time ago, it was claimed that Aurora, the network design of Aurora was a secret because it's a recipe for exascale computing. And he said that he doesn't see anything really new. And then he was wondering if there is anything new in the architecture of Aurora.
Yeah, if you look at the number of compute blades we have, the number of NICs we have, compared that to our system, you will quickly realize that Aurora is going to be like a lot more network endpoints, right? When we have the full system operating at scale, this will literally be the largest system with the most amount of network backend and the endpoints that are connected to each other. The secret sauce would basically come from the adaptive routing and the congestion control, right? Where you have different applications running together, and then how it manages that to basically give you the best bandwidth in both cases. So it's, I would say in some sense, there is nothing special, but in other sense, trying to put it all together at this scale is indeed special.
Yeah, I would agree with that. So the next one, Robert is asking, how do users select the options of like the GPU NIC transfer? I think that was a couple of slides back you were talking about that there.
Right. So there is options at different layers, right? So you have the lowest layer at the driver level. So you have the OFI layers where you can select for the network side. You have the level 0, which is the UMD side for the GPUs where you could select that. If you go above that, you have the MPICH CVARs that you could select various options for. And if you go even above that, you have the SYCL backend, which allows you to select a specific copy engine or specific device locations. So depending on which layer and how comfortable you are trying to focus and optimize and fine tune, you would find that there are different choices. Then again, this all comes down after you see basically an application and understand where the bottlenecks are, right? I mean, that there is infinite amount of knobs that you can fine tune and control, but do you really need that? And do you really have to use that? That's the question. And we have like this entire suite of profiling tools from the One API SDK, so vTune and Advisor, which will give you a bit of guidance on where you could utilize them better.
Okay, thank you. So the next one is, what is the penalty of moving data from NICs on the right side to memory on the left side? And he's saying CXI7 or HSN7 to memory near CPU 0.
Okay, so let me understand the question. So basically, the user wants to know if you go from CPU 0's NIC to CPU 1's NIC. So now you have two choices, right? Either you can go through the UPI and then basically move the data, or you can go outside through the switch, which is basically all-to-all connected within the chassis, right? So you can go to the switch and basically connect it directly and then move data this way as well. So that is also a choice. Again, what is better? You might get better latencies within the CPUs. But if you are going to try to move data in portions and only a portion of it needs to come back to this host, then going via the network would be better.
Thanks. Okay, so the next one is, how are the multiple NICs used on the blade? For example, if I do an MPI send receive between two nodes in the same rack, should I expect 1 NIC bandwidth or 4 or 8?
So you have algorithmic choices that you can set via the MPICH CVAR options. You have striping, which basically utilizes all the 4 NICs bandwidth, divides it among it, and then utilizes it. You could prefer, if your data sizes are very small, you could prefer just a single NIC to do the transactions. Or if you have different streams of data within your application and each of them needs different priorities, then you can dedicate specific NIC paths for that. So therefore, none of them is non-blocking. So again, you have choices, right? Like, it's not necessary that you need to opt for one or the other. So depending on what your application needs, you would be able to adapt it to however to utilize the system, basically with just a few environment options.
Okay. And Tim has a statement that he's put in the chat. And then the other one is Kaushik is asking if I have an IO intensive application running on over the 512 compute nodes. How do you recommend the placements of the allocation of nodes for the best IO performance?
IO to the backend storage or IO between the nodes itself?
I think it's just the intensive application. It says a storage.
You mean it means the storage or not? Yes, that's the point I
Yeah,
understand.
that's what he just added. He
Okay,
said,
so if you look at that, I think I didn't want to cover in this setup presentation, but if I go back to the Dragonfly topology, right? So you're going to start using the global links that connects to the backend storage systems to basically connect it, right? In any case, if you have the connectivity within the compute nodes, it's going to be faster, but you do have dedicated global links that connects from within each groups to the specific DOS group. And I mean, like placements, the whole point of Dragonfly topology, it's to allow you to be adaptive and to basically not worry about placements is what I think. But I mean, like you could always have and argue that if you have different applications trying to run together, placing them in parts of the system where you have more global links and spreading it out across the entire system will probably give you better bandwidth because you no longer are bottlenecked by the link at the tier 0, but more on the data transfer on the global link side. So basically then take one blade from each tier and then spread your workload as large as possible. Hopefully that answers your question.
yes, I think it did. Are there any more questions?
Okay, if not, if there are no more questions, then I'll go to my conclusion. Yes, that's why I want waiting for that part to finish.
Yeah, let's do that.
Yeah.
Thank you.
Okay, so I will start going to the conclusion, right? Like, I mean, like this all looks quite complex if you look at it in terms of architectural perspective, right? But what application users need to understand is this is by design, right? Like, I mean, any large scale system or any supercomputer that you take today, density of compute to data movement is quite a bit of challenge, right? For any one human architecture, you will always have the penalty of trying to basically optimize data movement to get better performance. Compute has never been the challenge, right? You have of a throughput machine where you can basically get as much compute as you want out of it. But the real problem comes when you have to schedule and move data between it. For Aurora, one of the quirks or one of the advantages and disadvantages is that you have multiple choices of how you move data between the different components. So therefore, that gives control back to the users instead of the architecture to optimize based on their bottlenecks, right? So that one thing that I would try to take away from this presentation is that try not to just overlap asynchronous communication between a single GPU and a CPU, but also between multiple GPUs within the single node. That way, you always try to work through if there is potential choking points within the system. You try to have a bit of asynchronicity so that allows you to get the better utilization of the entire blade itself, right? So with that, I think I finished a bit early. Hopefully that was useful. And if there are any other questions, I'm happy to take that now. Otherwise, back to you, Yasi.
Thanks, Servesh. I think that was really a great talk. So we still have another question. So
Go
controlling
ahead.
spin will be hard unless you have a whole machine for your run. The batch schedule puts your job on free nodes, but those are rarely spread uniformly over the racks. I think that's just more of a comments than
No,
a
that's
question.
not true, actually, right? You have the option to select specific tiers, right? The Dragonfly topology tiers, they are exposed to the system. So basically, what you can do is specify which tier you want to pick blades out. You can go even one step further and start picking out blades from the entire system, create your own scheduling logic, and then ask for an allocation that fits within that node topology, right? I mean, like it's just going to be more complicated on the user side to exactly map his workload to that. If you need to do it, yes, there's a possibility of always being able to do it. That shouldn't necessarily be stopping anybody from doing that. But however, you will have to wait until the scheduler finds those nodes are available and free and then schedules your job on top of it.
Yeah. Rob is asking, where do we find more documentation on controlling data paths?
So, I mean, let's just say these are all early systems, right? I mean, this is something that we could put together deck. I mean, this is something we will improve over the coming months or coming weeks, right? We are not in full production yet. We are still in the bring up phase. Like Yasi alluded, we are still having the work that we need to do. And I think we have done some basic documentation to get started. But once you go to optimizing data flows, there's a lot of nuances, and that's going to take us time for us to write through and provide lots more examples so that it's a bit more clearer to the users. So it's work in progress. Hopefully, we will do our best to work on that in the coming months.
Yeah, yes, that is true. And we currently do have a Aurora documentation that is on ALCF websites. So you can go ahead and do that. And we are actively working on it and adding more topics and content. Okay, so the next one is, which tools do you recommend to use to optimize the data flow?
So VTune is already aware of all the GPUs in a system, and it should tell you if you're bottlenecked by a particular compute or the data flow, and then you can optimize for occupancy, right? That should be good. If you want to look at basically you don't want to use VTune, you can go and look at perf Linux system counters and try to understand where these are for the CPU side. You can also, if you don't want to do any of this and you are an advanced user, you can go and look at the open documentation on the GPU side counters. And there's PTI GPUs, an open source repo, and Intel is good in that, where you have examples of directly writing your own performance layers to get the hardware counters from the GPU itself. So we have these three choices, and we are open to letting users pick and choose based on what best benefits them.
So the other one is, are the users expected to select memory use for DDR or HBM and the data path when moving data? How do you adopt like for these kind of things for Fortran, and if it's necessary to adopt the software?
You all must have programmed on Theta, right? Theta was more complicated, right? You had the MC DRAMs and you use NUMA-CTL to basically specify where the memory is, and Fortran codes work there. Similarly, here you have NUMA-CTL, and which basically allows you to pin and pick which memory and where you place it. For getting blades with a particular memory domain or a particular CPU configuration, we are going to work on trying to utilize a job scheduler to allocate blades dynamically based on the user's request. Once you have the blades, then you can use NUMA-CTL or libmemkind, one of these two, to allocate specific memory. If you don't want to deal with this, you can also opt for the cache mode, which basically hide the HBM behind the DDR, and therefore that will just let you get the most bandwidth. So there's always choices. If you want functionality, then you can get something to work immediately. But if you want to get more performance, then you can opt for the more finer grain optimizations.
Yeah. If not, I would like to thank Servesh and all of you for attending this session. We will be posting the slides and also the videos. And thank you all for joining, and thank you, Servesh, again for this great presentation.
Thanks, Yasi. Thank you all.